In this video, we're going to be talking about pH indicators in some more depth and what they are and how they work. So pH indicators are actually weak acids and bases themselves. We know that they change color at different pHs, which is why they're useful to us in titrations, that we use that as a visual signal that we have reached our equivalence point for an acid-base reaction. So what makes a pH indicator able to indicate in this way is that its acid form and its conjugate base form actually absorb different wavelengths of light. So that means that we perceive them to be different colors. We perceive something as having a color in solution when it absorbs some wavelengths of visible light, but not all. So the indicator that you are most familiar with is phenolphthalein. You've already used in titrations. It is colorless or clear in acidic and neutral solutions and turns magenta, turns pink, in basic solution. So I have the structure here of phenolphthalein, both in its acid form and its conjugate base form. You don't need to know these, you don't need to copy them down even, but I just wanted to give you an example of sort of what is actually going on in an indicator. They do tend to be relatively complicated organic molecules, organic chemicals, as you see here. So this is a different type of structure drawing that you're not used to, where each vertex is a carbon atom and there are invisible hydrogen atoms attached that fill up those carbon's octets. So that's why it just looks like a bunch of hexagons. But all that's really happening here is that above a certain pH, this hydrogen atom right here gets removed. So it is taken off between the left structure and the right structure. And that causes some other structural changes in the molecule as well. You can see that like this is connected down here, whereas it's not over here. And that is due to the electrons actually rearranging themselves as a result of that hydrogen being removed. And that change in the electronic structure of the molecule is what causes a change in the way it interacts with light. So the version on the left here, protonated form, does not absorb anything in the visible range. It absorbs in the ultraviolet. It absorbs higher energy photons. So that is why we perceive it as colorless, because all of the visible wavelengths pass right through it without being absorbed. This one we see as magenta because it is absorbing some visible wavelengths. Specifically, it is absorbing the yellow-green region of the spectrum most strongly. So essentially it's subtracting out the yellow and the green wavelengths, taking those out of the light, and what is allowed to pass through is mostly red and purple and blue, which is why we see this as a purplish magenta type color. Magenta is what your brain creates when it's seeing red and purple at the same time. So this change in structure causes a change in the way the molecule interacts with light, which we perceive as a change in color. So phenolphthalein is one of many, many indicators. And these are a few more examples. So phenolphthalein we can see here. So this is showing us what color these indicators appear at different pHs. The pHs are labeled up the top here. And these are just a handful of relatively common pH indicators. There are loads more. And it also gives the range over which, the pH range over which the color change happens. So this is telling us that the change occurs between pH 8.3 and 10. So 8.3 is where we get that very first hint of pale, pale pink. And by the time we reach pH 10, we are on full-on magenta territory here. But we can see that that range varies for different indicators. So methyl orange, for example, is red below pH 3.1. At 3.1 to 4.4 is where it's shifting from being almost entirely the red form to being almost entirely the kind of yellowy orange form. So we have orange in between, and then it's mostly yellowish above that 4.4. But this range is where that transition is happening. And we see that we have different ranges and different colors for all of the different indicators listed here. Universal indicator is up the top, is actually a mixture of several different indicators, and it changes color at just about every pH unit along the way, starting at red below about pH 4, green by the time you hit neutral, and then 14 or purple above pH 10 or so, all the way up to 14. So when you're designing a titration experiment, you always want to choose a pH indicator that is appropriate for the titration that you're doing. So we know that if you're reacting a strong acid with a strong base, the equivalence point is going to occur at pH 7. So phenolphthalein is sometimes used for that. That first hint of pink appears at 8.3, which is not too far beyond 7, especially since your pH is changing so rapidly near the equivalence point. Phenolphthalein is also commonly used for a weak acid with a strong base, where the pH of your equivalence point is a little bit above 7. Phenolphthalein can also be a good choice for those. But if you're doing a weak base with a strong acid where your equivalence point pH is actually below 7, phenolphthalein is not a good choice. You might want to pick something like methyl orange, where the range is lower. Methyl red is another one that's common. It's not on this diagram, but that is also commonly used for that. It's probably the most commonly used one actually for that particular combination. So we always want to make sure that we're taking into account what the titration is that we're doing, what pH our equivalence point will occur at, to choose an indicator that will work well, that will change as close to our equivalence point as possible. And generally it is preferable for your indicator to change just after equivalence point has been reached rather than just before.